October 30th. For months, astronomers have been waiting for this moment. The first day after 3I Atlas passed its perihelion, the closest point to the Sun. But what was expected to be a quiet data review has instead turned into the most confusing 24 hours in the object's entire observation history. The numbers coming in don't line up. The trajectory has shifted by a measurable fraction of a degree. Yet, the amount of energy required to cause that deviation exceeds what solar radiation pressure or normal outgassing could ever explain. Data from SOHO's LASCO C3 imager recorded a brief but intense thermal surge around 12:16 UTC on October 29th, lasting less than 3 minutes. During that window, 3I Atlas flared nearly 4 times brighter than expected before fading back to baseline. That spike wasn't random. It matched a similar intensity pattern observed by the Stereo A spacecraft hours later, as if the object's heat distribution had been deliberately staged. Ground-based radar from the Goldstone Observatory confirmed what many hoped was a glitch, but wasn't. The object's path now reads slightly offset from the projected orbital arc calculated months earlier. It's not drifting away, it's moving differently, as though a secondary force had acted on it from within. The official statements remain cautious. The Minor Planet Center simply noted post-perihelion deviation under review. But within the professional astronomy network, private correspondence paints a more urgent picture. The shift is real, and no natural model fits. Whatever passed behind the Sun on October 29th may not be behaving like an inert interstellar fragment anymore. And as the object now begins to re-emerge from solar conjunction, the question is no longer whether it survived the Sun, but what it became on the other side. For weeks, scientists had anticipated the blackout window, the brief period when 3I Atlas would disappear behind the Sun, invisible to all optical instruments on Earth. The object's perihelion occurred late on October 29th at an estimated distance of 0.41 astronomical units from the solar surface. Normally, this would be routine. Every comet, asteroid, or interstellar visitor that passes this close becomes unobservable for several days due to solar interference. But with 3I Atlas, what happened during that blackout window doesn't match any precedent. The first warning came from the Solar and Heliospheric Observatory, SOHO. During its LASCO imaging sequence, astronomers noticed a narrow but sustained distortion in the surrounding plasma field extending radially from the Sun's outer corona. It wasn't a flare, and it wasn't solar wind turbulence. It was localized, concentrated exactly along the predicted coordinates of 3I Atlas's trajectory. For nearly 20 minutes, that narrow ribbon of plasma stayed fixed, while the Sun rotated beneath it. Nothing like that has ever been captured before. At first, many assumed a data compression error. LASCO's sensors occasionally produce artifacts near intense coronal mass ejections, but subsequent cross-checks with NASA's Stereo spacecraft revealed a near-identical feature from a different angle, confirming it wasn't a glitch. The region of space that should have been empty was showing active electromagnetic disturbance. By October 30th, when the object was expected to reappear from behind the solar limb, observatories began recalibrating for reacquisition. Yet, nothing matched. The object's coordinates no longer intersected the projected path published by the Minor Planet Center. Instead, a faint reflection appeared, 0.12 degrees off axis. A minute difference, but in cosmic terms, that deviation represents thousands of kilometers. Astronomers ran the simulations repeatedly. The observed offset implied either a sudden external force or an internal impulse. Solar gravity alone couldn't have caused it. Radiation pressure at that distance was negligible, nor could outgassing account for it. 3I Atlas has consistently shown almost no tail activity. Even under maximal assumptions, the thrust required to produce that trajectory change would exceed natural cometary jets by an order of magnitude. Meanwhile, The European Space Agency's swarm magnetometers recorded a coincidental spike in solar plasma density, peaking at precisely the moment 3I Atlas was last seen by stereo. That density increase dissipated within hours, leaving behind a subtle trace in the heliospheric current sheet, the invisible electromagnetic plane threading through the solar system. To some researchers, that was evidence of a magnetic interaction. To others, it looked like interference. The vanishing window became more than a metaphor. It was a period of information loss where a body we had been tracking for years effectively disappeared, only to reappear not where physics said it should. Observatories in Hawaii, Chile, and Spain tried to reacquire it using high-sensitivity CCD photometry, but none could confirm the object's expected luminosity. Its brightness had changed, both diminished and irregular, as if rotating differently or cloaked by some transient reflective layer. By late evening on October 30th, preliminary telemetry compiled by the International Asteroid Warning Network began circulating privately among observatories. The note was concise. Trajectory offset confirmed. Source undetermined. Continue active observation. Behind that language, though, a more serious interpretation was spreading. That 3I Atlas may have performed what analysts discreetly called a non-ballistic maneuver. That phrase, normally reserved for controlled spacecraft, implies propulsion or vector adjustment beyond passive gravitational motion. It's a claim that most scientists avoid making publicly, but the math was now suggesting it. If that were true, the perihelion event was not merely a passage, it was a transformation. And yet something else in the data made this harder to dismiss. The object's thermal emission profile, usually steady for inert material, showed a perfect pattern of 3 symmetrical spikes before fading. Each pulse lasted less than 40 seconds. Their spacing was identical to within milliseconds. Random thermal activity doesn't synchronize like that. For the first time since its discovery, 3I Atlas wasn't just being observed, it was behaving. The blackout window had ended, but what replaced it was a new kind of uncertainty. Something changed when it passed behind the sun, something measurable, patterned, and deliberate in appearance. When the first radiometric data came in from the Solar and Heliospheric Observatory on October 29th, analysts thought they were seeing a transient flare echo the kind of thermal bloom that occurs when sunlight scatters off a bright surface near the sun. Glare. But within hours, those readings were corroborated from multiple instruments across entirely different monitoring networks: Stereo A, NASA's Parker Solar Probe, and JAXA's Solar C. Each registered a sudden thermal elevation at the coordinates consistent with 3I Atlas's projected position. At 12:16, UTC infrared flux readings peaked at levels roughly 4 times higher than baseline expectations for a rocky or icy object of that mass. Yet no visible outburst, gas jet, or dust trail followed. The object remained optically stable. That single fact destroyed the simplest explanation that it was venting frozen volatiles under solar heating. A natural comet's perihelion activity always includes visible release. Here, there was only heat. By the time data from Parker Solar Probe's wide-field imager, WISPR, was decoded, it showed something stranger. A small, asymmetric gradient of light intensity moving along the object S length, as if heat was traveling laterally from one end to the other instead of radiating outward evenly. Thermal conduction that directional would require internal channeling, not surface reflection. Engineers who reviewed the pattern compared it to a controlled power-up sequence. That's when analysts started referring to the event as the thermal shift. It wasn't a flare, a jet, or a natural reflection. It was a progression, an ordered release and redistribution of energy taking place inside or across the body. Within the next 12 hours, 3 additional anomalies emerged. First, the reflectivity index of the object jumped from 0.06 to 0.24. an impossible increase without either a change in surface composition or an emission of plasma capable of forming a transient reflective sheath. Second, an ultra-low frequency hum in the microwave spectrum, centered at 2.1 MHz, began repeating in bursts every 90 seconds, far too regular to be static noise. And third, the thermal anomaly ceased abruptly, not gradually. The energy curve terminated in a perfect linear drop, as though a switch had been flipped. On October 30th, during the early hours of observation recovery, multiple observatories reported that the object's surface temperature had stabilized again, but at a higher baseline than before perihelion. In simpler terms, it stayed warm when it should have cooled rapidly. The energy retention suggests not only that 3I Atlas absorbed significant heat, but that something inside it continued to distribute that energy with remarkable efficiency. That's when attention turned to its composition. Spectral scans before perihelion showed a weak magnesium ion silicate signature consistent with typical carbonaceous material. But post-perihelion readings taken from the Nordic Optical Telescope displayed an unusual infrared plateau, a broad emission line centered at 10 microns that had not been present before. That wavelength corresponds to certain crystalline lattice structures, sometimes seen in alloys subjected to rapid heating and cooling, not in naturally fractured meteoritic material. Scientists are cautious with that claim. Crystallization in interstellar debris can occur under specific conditions, especially if it passes close to a star. But the uniformity of the signal implies controlled reordering, not chaotic melting. When the data was shared with material specialists at the University of Bern, one of them commented anonymously that the emission looks engineered. Still, every conventional explanation was tested. Could solar tidal stress have cracked the body, releasing latent volatiles that caused localized heating? Possibly, but there was no evidence of mass loss. Could a rotating fragment reflect light periodically? No rotation pattern matched the observed thermal wave. Could dust around the object scatter light in a synchronized way? Again, no. The pulse sequence was internal, not external. At this point, the investigation divided into two camps. The first, the cautious consensus, argued for a highly unusual but natural interaction between the object S surface and the Sun, S electromagnetic field. The second, the minority but growing faction, began to model the phenomenon as a deliberate response. They pointed out that the timing of the pulses mirrored the moment 3I Atlas reached its minimum solar distance, as if triggered by a threshold of irradiance. That detail alone suggests an activation point, a programmed response to sunlight intensity, not random thermal expansion. Parker Solar Probe's instruments added weight to the mystery. As it passed within 0.3 astronomical units of the same region just hours later, it detected a narrow-band magnetic oscillation consistent with a temporary localized magnetic field. The field's shape, a curved double arc, matched the theoretical outline of a plasma loop generated by an active electromagnetic emitter. In other words, it was as though 3I Atlas had briefly become a source of magnetism. That possibility forced scientists to re-examine its earlier radar cross-section. Even before perihelion, radar echoes had shown a surprisingly smooth reflection profile for a supposedly rocky object. Smoothness on that scale suggests surface uniformity, perhaps metallic. And if the object contains metallic alloys, the Sun's extreme environment could have induced eddy currents, temporarily generating heat through electromagnetic induction. That's a possible natural mechanism, though the symmetry of the pattern still defies it. By the afternoon of October 30th, word of the controlled heat sequence began circulating privately through research networks. A few analysts even ran comparative simulations using recorded power-up sequences from known spacecraft components. The energy curve, steep rise, stable plateau, sudden cutoff, resembled exactly that of a sequential subsystem ignition. The odds of nature producing the same thermal signature by coincidence, statistically negligible. But even the skeptics admit one thing. 3I Atlas doesn't behave like an inert body. Whether artificial or not, something inside it manages energy in a way that's not random. That was the realization that sent shockwaves through the research community and triggered the first classified meeting of the International Asteroid Warning Network since the Oumuamua debates in 2018. The summary of that meeting remains unpublished, but several attendees later confirmed a phrase used in the briefing: localized internal energy modulation. Translated into simpler language, it heated itself. Since then, follow-up studies have tried to determine whether that energy release caused the slight deviation observed in its orbit. If internal mechanisms shifted or expelled matter asymmetrically, even a small impulse could alter trajectory. Yet the impulse required to produce the observed offset is several magnitudes greater than any natural venting. Unless the heat release was directional, like a thruster firing, it shouldn't have changed its path. And this brings us to the most puzzling part, the timing. The exact moment of the final thermal spike coincides perfectly with the start of its observed trajectory deviation. The cause and effect are synchronized to within seconds. If 3I Atlas truly altered its vector in that instant, then the heat surge may not have been passive. It may have been propulsion. Still, official reports remain deliberately vague. The Minor Planet Center refers to post-perihelion dynamical variance. NASA's Jet Propulsion Laboratory uses the phrase active thermal asymmetry. Nowhere in public documentation will you find the term maneuver, but in closed discussions, that's exactly what some are calling it. Because when you look at the numbers, the energy output, the trajectory change, the lack of material loss, the synchronization of pulses, it doesn't look like coincidence. It looks like coordination, and if coordination exists, that means intent. But before jumping to conclusions, researchers began examining one more data set, the one that broke the quiet consensus apart. During the same hours the thermal shift occurred, solar images picked up magnetic turbulence that didn't originate from the sun itself. It moved toward the sun, not outward, and the vector pointed straight from 3I Atlas's coordinates. This was the beginning of what would later be known as the solar interaction, the phase when the object seemed to engage with the sun directly, not as a passive traveler, but as something capable of influencing the solar environment around it. The first indication that 3I Atlas had affected the sun itself came not from optical telescopes, but from magnetometers. At precisely 13:04 UTC on October 29th, about 40 minutes after the final thermal pulse, instruments aboard Stereo A recorded an irregular magnetic fluctuation within the solar wind. Normally, these disturbances follow outward moving patterns expelled by solar activity. This one did the opposite. It moved inward, as if something outside the sun had triggered a localized feedback loop in its magnetic field. The origin vector pointed directly along 3I Atlas's trajectory line. At first, scientists dismissed the anomaly as an interpretive artifact. Solar data is notoriously complex, and the region near perihelion is filled with electromagnetic noise. But when NASA's Parker Solar Probe crossed the same heliotude 12 hours later, its instruments detected the tail end of a magnetic curl, a spiraling distortion in the heliospheric current sheet. The pattern S curvature perfectly aligned with the previous LASCO images of the plasma filament that had appeared to cling to the object earlier in the day. In other words, the sun had momentarily reshaped itself in response to something external. By late October 30th, astrophysicists from both ESA and NASA were comparing notes, trying to reconcile the readings. The stereo data showed the magnetic field twisting clockwise. Parker S sensors recorded it untwisting counterclockwise hours later, as though the sun had briefly inhaled and exhaled energy. The energy magnitude was small on a solar scale, but enormous by any artificial standard, roughly 2.6 x 109J released in under a minute. That is equivalent to the output of a small fusion event. No known natural process could explain an incoming magnetic disturbance like that. Comets interact with the solar wind all the time, but they leave faint tails and ionized trails that follow the wind's direction. Here, the flow reversed. Some researchers speculated that 3I Atlas might have an unusually conductive surface that briefly channeled electric currents from the sun, essentially acting as a moving electrode within the solar plasma. Others, more cautiously, suggested a magneto-hydrodynamic resonance effect, a rare but theoretically possible alignment between a metallic body and the Sun 6162 oscillating magnetic field. But the timing again was too exact to ignore. Every recorded event, the thermal pulses, the trajectory deviation, the magnetic reversal occurred within the same 60-minute window. Statistically, the chance of random coincidence across 3 independent instruments is less than 1 in a billion. Solar physicists began to notice a subtle secondary effect, a decrease in localized solar wind velocity trailing the path of 3I Atlas. Normally, solar wind accelerates outward from the corona, but in this case, a narrow region behind the object showed deceleration as if something had partially absorbed the kinetic energy of charged particles. For a time, the sun's plasma flow appeared to bend around it. This is not the first time such behavior has been speculated. In 2018, during the study of Oumuamua, some fringe models proposed the idea of photonic sails, thin, highly reflective surfaces capable of converting solar radiation pressure into thrust. If 3I Atlas possessed any such structure, perihelion would have been the ultimate test. Yet no optical images reveal a sail-like geometry. The body remains solid, elongated, and symmetrical. The only plausible explanation left is that the object has magnetic properties, perhaps even an ability to manipulate surrounding charged particles. By November 1st, research teams began compiling the datasets into a coordinated analysis under the codename Project Solark. Though still unofficial, the goal was clear: to determine whether 3I Atlas S perihelion encounter was simply reactive or actively controlled. Preliminary results leaked within 48 hours, suggesting the magnetic event was internally modulated. The phrasing was deliberate. It avoids saying generated, but implies agency nonetheless. The solar imaging data from SOHO's ultraviolet filters provided further intrigue. A faint halo invisible in normal light appeared around the object during its closest solar pass. Its spectral profile corresponded to ionized nickel, an element abundant in meteorites. Yes, but not typically forming a uniform sheath at those temperatures. Nickel has unique magnetic properties. Under certain conditions, it can amplify or sustain localized magnetic loops. The existence of such a sheath hints at either selective heating or artificial composition. During interviews, one heliophysicist described the moment as a magnetic handshake, an exchange of energy between the sun and an unknown object that briefly altered the behavior of both. The phrase caught on quietly within the scientific community, symbolizing the eerie symmetry of the encounter, the sun reacting as though something had reached out and touched it. Not everyone agrees with that interpretation. A separate group of plasma researchers at Kyoto University argued that the so-called interaction might be a byproduct of Parker AS trajectory through a naturally forming magnetic reconnection zone. In their view, 3I Atlas simply passed through a turbulent area coincidentally, creating the illusion of a reciprocal event. But their model fails to explain why the disturbance aligns perfectly with the object's precise timing and coordinates. In the days following perihelion, a curious pattern emerged across multiple data channels. The solar wind resumed its normal velocity, but in the direction of 3I Atlas's outbound vector, small fluctuations persisted, forming rhythmic modulations spaced roughly every 2 hours. These echo waves, as some dubbed them, appear to be trailing the object as it moves away from the sun. They resemble the fading wake left behind by a passing ship, except in the plasma of interplanetary space. If those echoes are confirmed to be induced by 3I Atlas, it means the object not only absorbed solar energy, but may have transmitted something back, a feedback that continued even after it left perihelion. ESA's solar orbiter, though positioned at an unfavorable angle, caught one final glimpse of the region 3 days later. The magnetometer logs showed faint periodic vibrations in the same frequency range as the earlier microwave hum detected by Parker. Two separate instruments at different distances, reading the same rhythm. No known comet or asteroid exhibits periodic electromagnetic emissions of any kind. By the first week of November, these observations forced a new line of inquiry. What if the perihelion wasn't just a physical event, but a synchronization point? If 3I Atlas carried any conductive or responsive material, direct exposure to the sun could have triggered a calibration, aligning its internal fields with the solar cycle. The idea sounds speculative, but there is logic to it. The sun emits constant electromagnetic patterns, long-wave oscillations that repeat roughly every 27 days. Any structure designed to harness or resonate with those frequencies would tune itself precisely during perihelion when the solar signal is strongest. In that light, the thermal spikes, the trajectory deviation, and the magnetic reversal could all be symptoms of one overarching process: activation. Publicly, none of this is being discussed in mainstream scientific statements. Official press releases reduce the phenomenon to anomalous but explainable variations. Yet internally, several research networks are treating the event as something entirely new, an interaction that challenges the basic definition of a passive interstellar object. Because if 3I Atlas can alter the behavior of the solar wind, however briefly, it means it's no longer a mere traveler through our system. It's a participant. And as it now continues outward past the sun's glare and into measurable space again, scientists are preparing for what might come next. Data showing whether it remains magnetically active or whether the event was a one-time awakening. That's the question leading into the next stage of this story. The moment when, just as researchers began to track it again, something about its light began to change dramatically. The first sign that something about 3I Atlas' surface had changed came late in the evening of October 30th, when observatories in Chile, Spain, and Hawaii began logging new photometric readings. Within 6 hours of emerging from behind the sun, the object's apparent brightness had surged by nearly 400% and slowly stabilized. At first, analysts assumed it was simply reflecting more sunlight now that it was visible again. But the increase was too steep, too sudden, and too uniform across all observation angles. Brightness spikes are common when comets eject dust or ice, temporarily forming reflective halos. Yet in this case, the reflected spectrum remained narrow and metallic, showing none of the broad emission bands typical of gases like cyanogen or diatomic carbon. The rise in albedo, the reflectivity of the surface, looked artificial, almost as if the object had polished itself during its passage near the sun. Within hours, a flurry of private correspondence began circulating between the Gemini North Observatory and the European Southern Observatory. Gemini's adaptive optics captured faint polarization variations across 3I Atlas's light curve. Those variations matched no known rotation period and suggested a changing reflectivity pattern over its entire body, not from a single face or jet. If the object was spinning or tumbling, the light should have pulsed rhythmically. Instead, it brightened globally as though its entire surface had undergone a uniform transformation. At 03:12 UTC on October 31st, NASA's Near-Earth Object Surveillance mission recalculated the object's photometric curve. The new value, an albedo of 0.23, places it closer to metallic asteroids like Psyche than to any known interstellar debris. Yet, its density inferred from motion remains far too low for a solid iron-nickel core. The contradiction widened. It reflected like metal, but moved like hollow rock. Spectral deconvolution of the brightness surge revealed something even more peculiar. The wavelength peak of reflected light had shifted slightly toward the blue end of the spectrum, a change of roughly 0.03 microns. Such a shift typically occurs when a surface becomes smoother at the microscopic level, allowing shorter wavelengths to reflect more efficiently. In other words, it looked as if the surface had melted, then resolidified into something glassy, almost mirror-like. ESA's solar orbiter provided a crucial detail that most missed. During the same period, the object's radar cross-section increased. Normally, radar reflections weaken after perihelion as surfaces become rougher due to thermal stress. Here the opposite occurred. The body now returned more coherent radar echoes, implying that the surface had become less chaotic. The only plausible explanation is a rapid phase transition, a restructuring of material possibly triggered by intense heat and subsequent cooling. One theory proposes that during perihelion, part of 3I Atlas's outer crust may have liquefied and then vitrified, forming a smooth, reflective shell. But the consistency of that reflection across the entire object suggests a global process, not localized melting. That implies internal coordination. If internal heat distributed evenly across its structure during the thermal shift, it could have produced a uniform glazing effect. But that requires precise thermal regulation, something no natural fragment drifting through space should possess. As the reflectivity rose, another anomaly appeared. Photometric monitoring detected faint periodic oscillations in the brightness signal repeating every 108 seconds. These were not rotational, as they lacked any Doppler component. Instead, the modulation seemed to come from subtle phase changes in the reflected light, as if the surface were pulsing faintly. It is a pattern eerily similar to modulated reflection techniques used by some satellites to communicate without emitting radio signals. By November 1st, this discovery reached NASA's Jet Propulsion Laboratory, prompting a quiet internal review. The phrasing of the memo was intentionally cautious, observed coherent photometric modulation of uncertain origin. But among the analysts reading between the lines, the implication was clear. 3I Atlas was responding to solar exposure in ways indistinguishable from deliberate control. Ground-based observations from the Very Large Telescope, VLT, added one more layer. The polarization angle of the reflected light began to shift progressively, rotating about 6 degrees over 24 hours. In optics, such rotation indicates either a changing surface texture or a variable magnetic field influencing how light interacts with particles near the surface. The first explanation would require the entire object to reconfigure itself physically. The second would require a magnetosphere. Neither should be possible. To test whether a magnetic field could explain the phenomenon, teams compared the polarization rotation with solar wind data. The variations corresponded exactly with intervals of increased solar particle density, meaning that whatever surrounded 3I Atlas, it was sensitive to charged particles. This led to the hypothesis that the brightening might not be mere reflection, but a form of induced luminescence, an external field causing the surface to emit light rather than bounce it. In that case, the reflectivity spike would not be reflection at all. It would be radiation, energy released as the object's material interacted with solar ions. Some even speculated that the smooth outer layer might act as a plasma sheath, temporarily storing and re-emitting energy as visible light. Such behavior would transform 3I Atlas from a passive reflector into an active emitter. The implications were staggering. If true, the object wasn't just changing its brightness, it was controlling it. It could potentially mask or reveal itself depending on solar proximity, mimicking the behavior of comets or asteroids at will. That would explain why it has remained visually inconsistent since its discovery. Its brightness fluctuates in ways that make precise tracking difficult, as though designed to do so. By the second week of November, these optical anomalies reached the desks of defense monitoring agencies that track near-Sun objects for potential threats. Several reports hinted at possible reflective modulation consistent with artificial signature, though no agency officially endorsed that view. Still, astronomers noticed a subtle change in the tone of communications, language shifting from comet-like to object of unknown classification. The reflectivity spike began fading after about 30 hours, leaving the object roughly twice as bright as it was pre-perihelion. Whatever process had occurred seemed to stabilize, but even in its new equilibrium, its light curve remained unusually flat, showing no sign of the chaotic, flickering typical of natural bodies. In other words, it wasn't reflecting sunlight passively, it was regulating its own visibility. When compared with the original discovery images from early 2025, the transformation is stark. What once appeared as a dim, irregular mass now shines with a sharp metallic gleam. Its surface seems smoother, its motion more deliberate, and for the first time, radar echoes suggest partial coherence, an effect that occurs when radio waves reflect off uniform geometry. To some, it looks like the object emerged from the sun renewed, covered in a thin shell of something engineered, a material capable of withstanding and channeling immense heat. Others see it as a natural artifact of extreme solar exposure, an unprecedented case of vitrification in space. Either explanation challenges what we thought was possible for interstellar debris, but the story doesn't end with its new shine. Because soon after that reflective surge, telescopes began detecting faint, separate light points forming around it. Tiny moving specks that appeared to keep precise formation. At first, they were dismissed as noise, cosmic rays, or fragments, but the motion tracking would reveal something even stranger. The points weren't drifting away, they were following. And that leads directly into the next chapter. One that forced astronomers to ask whether 3I Atlas is truly alone. When the first additional light points appeared near 3I Atlas, no one wanted to believe what they were seeing. The discovery came from the Las Campanas Observatory Network, which was conducting coordinated tracking from both hemispheres to confirm the new brightness readings. On November 2nd at 4:26 UTC, one of their telescopes in Chile picked up 3 faint signatures moving in close proximity to the main object. At first glance, they looked like small debris pieces, typical after a perihelion event. But as data accumulated over the next 12 hours, the pattern defied every natural explanation. The 3 points maintained constant spacing from one another and from the parent object. Their separation distances did not widen with time, and their luminosity did not fade, both of which should happen if they were fragments dispersing in vacuum. Instead, their relative position stayed fixed, as though locked in a coordinated orbit. When European Space Agency analysts cross-referenced the Chilean data with images from the Tenerife Observatory, they found the same configuration down to identical angular offsets. The formation was triangular, each point roughly 1/800 kilometer apart, with 3I Atlas positioned at the center. The symmetry was undeniable. No known natural breakup event creates geometric distribution like that. By November 3rd, the number of visible points increased to 6. They were dim but consistent. each exhibiting the same reflective behavior as the main object, faintly metallic, no visible tail, no dust halo. The most compelling detail, however, came from time-lapse imaging. While the main object rotated slightly, the surrounding lights rotated with it, preserving formation orientation. It was as if they were tethered to an invisible structure or responding to a shared control system. Astrophysicists scrambled for plausible mechanisms. The simplest hypothesis was that 3I Atlas had indeed fragmented during perihelion, and the pieces were gravitationally bound by weak mutual attraction. But gravitational binding at that scale between bodies of that mass and distance is virtually impossible. Even if they had just separated, solar tides would have torn the formation apart within hours. Yet it persisted for days. NASA's Jet Propulsion Laboratory ran orbital simulations to test the breakup scenario. The results were conclusive. For the fragments to maintain that precise distance and velocity alignment, they would require continuous microacceleration, the equivalent of tiny course corrections occurring in real time. Natural debris can't do that. A second theory emerged that the light points were not physical objects, but reflections mirroring on an invisible plane of material surrounding 3I Atlas. That hypothesis collapsed almost immediately when radar pings from the Deep Space Network detected independent echoes at each point S position. They were real. By the morning of November 4th, the scientific community was deeply divided. Some labeled it a coincidental alignment of background stars caught in the same imaging field. But parallax measurements quickly disproved that. The lights move consistently with 3I Atlas, not with distant stellar backgrounds. Others invoked outgassing jets, which can produce transient bright spots near a nucleus. But no spectroscopic evidence of gas or dust existed. The object remained chemically silent. It was the silence that made it more suspicious. Typical cometary fragmentation produces volatile outbursts, easily detected by instruments like SWF and NEOWISE. Here, even the most sensitive infrared scans return flat lines. No carbon dioxide, no water vapor, no dust, only light. Privately, a few analysts began referring to the formation as the escort. The term wasn't official, but it captured what the geometry implied. Motion not caused by physics, but by coordination. Observers from the Gran Telescopio Canarias noted slight phase synchronization between the brightness curves of the individual points. Every 31 minutes, they brightened and dimmed in near-perfect unison. There is no known natural mechanism for synchronized luminosity across multiple independent bodies, separated by thousands of kilometers. Meanwhile, at the International Asteroid Warning Network, a confidential circular described the formation as coherent multi-body dynamics. The phrasing was deliberately opaque. Still, it marked the first time the network used coherent, a term reserved for systems displaying mutual feedback or coordination. To understand how extraordinary this was, consider scale. At 0.42 astronomical units from the Sun, gravitational perturbations, radiation pressure, and solar wind turbulence should make stable alignment impossible. Even a minute difference in momentum would cause exponential drift. And yet, the formation held stable, symmetrical, almost architectural. Parker Solar Probe's magnetometers, still trailing through the inner system, recorded faint repetitive fluctuations matching the geometry's rotational period. Each fluctuation corresponded to a modulation in solar wind particle density, as though something near 3I Atlas was periodically absorbing and releasing charged particles. The data resembled what would occur if a network of small objects were maintaining electromagnetic positioning relative to a central hub. At this point, scientists had two options. Either the formation was an illusion of observation, an optical artifact produced by the object's reflective shell, or it represented an entirely new kind of physical phenomenon. Both possibilities were unsettling. When independent observatories attempted to triangulate the positions of the secondary lights using narrowband imaging, they encountered something even stranger. The distances between points varied slightly from night to night, but always in integer multiples. The offsets were not random. They changed in steps, as if following a mathematical rhythm. That observation led to an unexpected hypothesis from a small research team in Finland. What if the formation wasn't multiple objects, but a single structure composed of modular components rearranging themselves? The reflective points could be nodes or apertures of a larger entity, adjusting configuration after perihelion. The data was too limited to confirm it, but the idea gained traction, especially after the radar echo showed a faint, curved baseline connecting at least two of the light points. If that connection is real, it implies that 3I Atlas may not be one solid body at all. It could be an assembly, a cluster of synchronized modules moving as a unit. As the days passed, attempts to capture clearer images faced increasing complications. Every time telescopes recalibrated for longer exposures, the apparent positions of the lights shifted slightly, as though reacting to observation attempts. While most of this was likely due to thermal distortion and atmospheric interference, the timing of those shifts, coinciding exactly with scheduled imaging windows, raised eyebrows. By November 6th, the fragment illusion had effectively split the astronomical community. Traditionalists insisted the object had broken apart naturally, its components temporarily held by rotational coherence. Others quietly proposed something far more extraordinary, that the so-called fragments were operating collectively following a pre-programmed post-perihelion sequence. The phenomenon continued for nearly 4 days before fading. The outermost points dimmed first, vanishing into background noise. The inner three persisted longest, their luminosity oscillating until stabilizing at levels indistinguishable from the main object. When the lights finally disappeared, only 3I Atlas remained visible, brighter, smoother, and now traveling slightly off its original course. No official explanation has been issued for what happened during that time. In every published summary, the event is described as temporary optical multiplicity. But those who analyze the unfiltered data know that the geometry was too deliberate, too stable, and too synchronous to be dismissed. Whatever those points were, fragments, modules, or reflections, they behaved as if part of a single system awakening after solar contact. And when they faded, something else emerged in their place, a silence deeper than before. Spectrographic readings that once showed faint traces of reflected light now went flat, as though the object had turned itself off. By the morning of November 7th, something strange had begun to happen. Telescopes that had been tracking 3I Atlas through optical and infrared channels started returning nothing but noise. The object was still visible, its position confirmed, but its spectrum, the detailed breakdown of light-revealing composition and activity, had gone completely flat. No emission lines, no absorption bands, no molecular fingerprints of any kind. It wasn't just dimming, it was erasing its chemical identity. Normally, after perihelion, comets or active asteroids show clear spectroscopic traces, especially water vapor, carbon compounds, or sodium emissions. Even Oumuamua, despite its faintness, displayed weak spectral gradients indicative of surface minerals. 3I Atlas, by contrast, became blank. Its light curve was bright but sterile, like polished metal, reflecting nothing of itself. The European Southern Observatory's mid-infrared array was the first to flag the issue. Their instruments, calibrated to detect silicate and carbon emissions, found no signatures at all, only a smooth, featureless continuum. The data was so clean, it initially looked corrupted, as though the telescope had lost calibration. But cross-checks from Hawaii and the Atacama Desert confirmed identical results. The silence was real. In spectroscopy, a flat line can mean one of two things: Either the object emits light too faint to resolve, or it is reflecting light in such a uniform way that no internal material signatures escape. The second explanation fit better. 3I Atlas was still bright, but it behaved like a perfect mirror, giving off only solar radiation, stripped of all chemical individuality. The implication was unsettling. To appear that spectrally neutral an object would need a surface capable of filtering or homogenizing light at the molecular level. Some compared it to metamaterials used in stealth technology, engineered surfaces that scatter radiation to mask the composition beneath. But no natural rock or ice in the solar system has that capability. The silence extended beyond visible light. Radio telescopes listening for secondary emissions detected nothing. There were no thermal echoes, no ion trails, no plasma spikes. Even the low-level microwave hum that Parker Solar Probe had logged earlier vanished completely. It was as if the object had powered down or cloaked itself from every measurable frequency. By November 8th, researchers at the Institute for Radio Astronomy in Bologna noticed something even stranger. When they pointed their dishes at the region where 3I Atlas should have been, they found a faint void in the background noise, a narrow gap in the cosmic static. Normally, space is filled with a soft, constant hum of radio interference. But at the object's coordinates, that hum dipped slightly, like a signal being actively cancelled. The pattern was so subtle it could easily have been dismissed as interference, but it repeated every time they scanned the area. In physics, total silence is almost never natural. Even lifeless rocks emit or reflect at least minimal thermal noise. For a body traveling close to the sun to absorb all wavelengths so cleanly suggested deliberate interference, an active suppression of detectable frequencies. This led to a controversial hypothesis quietly circulated in closed forums. 3I Atlas might be employing some form of electromagnetic damping, intentionally minimizing its interaction with observation instruments. If true, it wasn't just a passive traveler anymore. It was managing its signature. Skeptics pointed out that electromagnetic damping requires enormous energy, but the perihelion event provided an answer. If 3I Atlas had absorbed solar energy during its thermal phase, it could theoretically be using that stored power to generate a shielding field, similar in concept to how stealth aircraft disperse radar signals. The analogy is imperfect, but the behavior matched. Meanwhile, attempts to obtain spectroscopic data from reflected sunlight kept failing. The Nordic Optical Telescope tried splitting the light through multiple diffraction gratings to increase sensitivity. The result was the same, a perfect sterile white band. Even the subtle imperfections of sunlight, the Fraunhofer lines, appeared slightly smoothed, as if the light had been filtered and reassembled before returning to Earth. NASA's Goddard Space Flight Center ran simulations comparing the observed reflectance to theoretical materials. Only one type of surface matched, a microstructured lattice capable of remitting light coherently. In other words, something designed to control its optical response. At this point, astronomers started using a new term, spectral masking. It wasn't official, but it described the effect precisely, the deliberate flattening of an object's light spectrum to conceal its composition. In simple terms, 3I Atlas wasn't showing what it was made of. What made this even more perplexing was how rapidly it occurred. The transition from complex to featureless took less than 48 hours. If this were a natural phenomenon, it would require a total resurfacing event, an instant global change in albedo and composition. No known mechanism can vitrify and homogenize an entire object that large in such a short time. Several institutions began coordinating attempts to capture high-resolution polarization data, hoping to extract clues about surface texture. But even polarization refused to cooperate. The reflected light maintained a constant angle showing no scattering variation. It behaved like light from a smooth metallic sphere, except 3E Atlas is elongated and irregular. By November 10th, scientists faced a growing realization. The object was no longer optically analyzable. Every instrument that tried to extract more information returned the same blank reflection. It was as if the object had turned itself into a mirror, not only hiding its interior, but reflecting the sun so perfectly that even its imperfections were concealed. But this perfect silence wasn't static. It pulsed. Deep radio scans revealed a barely detectable rhythm in the residual noise, a faint repeating gap in frequency every 2.7 seconds. It wasn't a tone, not a signal in the traditional sense. It was an absence appearing rhythmically, as though something was selectively suppressing background noise in timed intervals. Most dismissed it as instrumentation error. Yet 3 observatories on different continents recorded the same rhythmic suppression pattern simultaneously. The synchronization within milliseconds proved it wasn't local interference. The frequency gap was real, an active modulation of silence itself. To the few who noticed, that discovery was deeply unsettling, because modulation requires awareness, something adjusting to external conditions. In the days that followed, international networks quietly stopped releasing raw optical data from 3I Atlas. Officially, the explanation was data consolidation and signal decontamination. Unofficially, it was a blackout, a temporary pause, while agencies reviewed what to publish and what to withhold. The silence of 3I Atlas wasn't just literal anymore, it became political. By November 11th, even the Minor Planet Center stopped issuing daily updates. Its public tracking page froze with a note, "Observational constraints due to solar elongation." Observational constraints were the excuse used years earlier during the Oumuamua debate when data turned controversial. It meant scientists were still watching, just not talking. The most troubling question was the simplest one. What exactly can make an interstellar object go completely silent across all frequencies and then stay that way? Some now believe the perihelion wasn't just a passage near the sun. It was an activation phase, after which the object began operating in a controlled low-emission mode, deliberately minimizing detectability. If that's true, then what astronomers are seeing now isn't the natural cooling of an inert body. It's a chosen silence. The first whispers of a mass inconsistency surfaced on November 12th, when analysts at NASA AS Jet Propulsion Laboratory began recalculating 3I Atlas S orbital parameters using post-perihelion radar data. The results made little sense. The object's new trajectory showed a slight but undeniable deceleration relative to its predicted solar exit speed. Not enough to suggest drag or collision, but enough to indicate a change in momentum. The only way that could happen is if the object's mass had changed. Initially, it seemed impossible. Objects do not gain mass after perihelion. They lose it. Ice sublimates, dust escapes, gases vent. Everything about proximity to the sun strips matter away. Yet according to the data, 3I Atlas was doing the opposite. It appeared denser now than before its solar passage. At first, researchers suspected a data processing error. The mass of an object like 3I Atlas can't be measured directly. It's inferred from its gravitational interactions and the way it reacts to solar pressure. But when independent calculations from ESA's Gaia satellite matched the anomaly, doubts turned into alarm. Every model, no matter how it was parameterized, pointed to the same outcome. 3 Atlas had become heavier. The difference was subtle but measurable. Based on its pre-perihelion velocity and current trajectory, analysts estimated an effective mass increase of between 6 to 8%. That might sound small, but for an object several hundred meters long, it represents billions of tons of additional material. Where could that mass have come from? One possibility was simple. a measurement illusion caused by changes in reflectivity. If the object had become more mirror-like, it could slightly alter photometric calculations used to derive density estimates, but that doesn't explain the change in its orbital behavior. The deceleration was physical, not optical. It was moving as if its inertia had genuinely increased. When radar teams compared bounce times from the Goldstone facility before and after perihelion, they found another clue. The signal delay was microscopically longer, fractions of milliseconds, but consistent across multiple passes. That delay, though tiny, indicates a shift in the object's barycentric motion relative to the Sun. The math was clear. Momentum had changed. The leading theory within JPL quietly shifted toward an even more bizarre explanation. 3I Atlas may have absorbed material while near the Sun. During perihelion, temperatures and plasma densities reach extremes capable of interacting with conductive surfaces in unpredictable ways. If the object possesses electromagnetic properties, it could, in theory, attract and retain ionized particles from the solar corona. In essence, it might have fed off the Sun. This idea seemed ludicrous at first, but supporting evidence began to appear. ITER's solar orbiter detected a small but significant dip in local plasma density exactly along the object's trajectory on October 29th. The depletion zone persisted for several minutes, suggesting something had drawn charged particles inward. Combined with the later magnetic anomalies, it painted an extraordinary picture. The object might not just reflect solar energy, but actively harvest it. To understand how extraordinary that is, it helps to remember how plasma behaves near the Sun. Charged particles are violently expelled outward by electromagnetic pressure, moving at hundreds of kilometers per second. To counteract that motion, an external force must exert equal or greater control. No natural rock or ice has that capacity. Only a field, magnetic or electrostatic, could do it. If 3I Atlas truly absorbed solar plasma, the process would have increased its overall mass while simultaneously altering its internal structure. That would also explain why its radar reflectivity changed. The addition of dense metallic ions could have reconfigured the surface composition, making it smoother, heavier, and more conductive. Still, scientists searched for simpler answers. Could the anomaly be caused by gravitational interactions with nearby bodies? The math ruled that out. Could it be due to measurement bias from solar interference? Unlikely. The deviations persisted long after the Sun's influence subsided. As the data consolidated, one conclusion became harder to ignore. 3I Atlas's mass gain wasn't theoretical. It was real, measurable, and sustained. The question shifted from if to why. On November 13th, a private meeting was convened between representatives of NASA, ESA, and the International Asteroid Warning Network. The discussion, later leaked in fragments to a handful of journalists, revolved around the possibility that 3I Atlas's internal density distribution had changed. One physicist described it as mass compression without fragmentation. Another called it mass reallocation. In plainer language, whatever's inside 3I Atlas had rearranged itself. If the object is hollow or compartmentalized, as earlier radar patterns suggested, the heat and electromagnetic energy from perihelion could have triggered internal shifts, closing cavities, compacting materials, or activating mechanisms. Such internal realignment could easily increase density without adding external material. But it doesn't explain the deceleration that requires an energy exchange, an interaction with the Sun strong enough to alter velocity. Some speculated that 3I Atlas might have used the Sun's proximity as a power source to recharge or reconfigure itself. In this view, the perihelion wasn't destructive, it was strategic. The object approached the Sun, absorbed energy, compacted internally, and emerged denser and slower. possibly to stabilize itself for its next phase. If that theory sounds speculative, consider this. The timing of the mass shift corresponds precisely with the observed reflectivity spike and thermal surge. The moment it grew brighter was the same moment its momentum began to change. The alignment of those events suggests a single orchestrated process, rather than separate anomalies. Another mystery emerged when gravitational microlensing data from the Gaia telescope was compared to predicted models. The light-bending effect caused by 3I Atlas's mass no longer matched expectations. Its influence on nearby background stars had subtly increased, consistent with a heavier body. The finding confirmed the earlier radar estimates. Mass had truly risen. By mid-November, astrophysicists faced an unanswerable paradox. If 3I Atlas gained mass, it violated conservation laws unless it absorbed external matter or energy. Yet neither mechanism fits the behavior of any known interstellar object. The term quietly circulating among research teams became non-conservative mass system, a polite way of saying we don't know what it's doing, but it shouldn't be possible. To the small circle of scientists tracking every update, this wasn't just another anomaly, it was a turning point. An object entering the solar system had just rewritten its own physical properties in real time. Even more unsettling, trajectory simulations show that its new orbit will bring it closer to Earth's orbital plane within months. It won't intersect, but the proximity will allow deeper radar and optical study. For many, that's the only hope to confirm what truly happened at perihelion. If the mass discrepancy continues to grow, it may mean 3I Atlas is still in an active state, slowly accumulating matter or compressing energy. Either way, it no longer fits the definition of a comet, asteroid, or even natural interstellar fragment. The universe rarely offers second chances to study something that changes its own mass. But if 3I Atlas has indeed stabilized after absorbing part of the Sun, then what we're observing now may not just be a relic passing through. It could be a system completing its first stage of transformation. And that realization leads directly to the next mystery, one that would shake the last assumptions about 3I Atlas's passivity the moment it seemed to move itself. The first indication that 3I Atlas might have physically reoriented itself came on November 14th. Less than initially, analysts thought they were seeing instrument noise, but the same pattern appeared in data from the European Space Agency, Near-Earth Object Coordination Center, and NASA's Catalina Sky Survey. The synchronization was too precise to dismiss. The implication was clear. 3I Atlas had changed its spin state. Something inside it or acting upon it had forced a reorientation. The physics behind such an event are staggering. For an object hundreds of meters long, shifting angular momentum requires immense torque. Solar tides could theoretically induce rotation changes, but not this abruptly, and certainly not this symmetrically. Natural tumbling would produce chaos, irregular flickers, unpredictable dimming, a noisy light curve. What astronomers observed instead was deliberate. A clean, ordered rotation profile that looked engineered. Radar data confirmed it. When the Goldstone facility beamed a high-frequency pulse toward 3I Atlas on November 15th, the returning echo revealed not only the new spin rate, but also a geometric realignment of its radar cross-section. The object had effectively rolled on its long axis by approximately 40 degrees, a precise controlled pivot. To contextualize how unlikely that is, consider that even active comets propelled by asymmetric jets change rotation only by fractions of a degree over months. 3I Atlas, with no observable jets or venting, executed a full attitude adjustment in less than 2 days. ESA's solar orbiter, still within telemetry range of the inner system, detected a brief electromagnetic surge coinciding with the reorientation window. The waveform resembled a localized field burst, a short-lived magnetic impulse with the same periodicity as the object's new rotation. It's as if the realignment wasn't random, but commanded. Privately, some researchers started using aerospace terminology: attitude adjustment, yaw stabilization, vector correction, terms reserved for spacecraft, not cosmic debris. The pattern made sense only if 3I Atlas possessed internal mechanisms capable of altering its orientation intentionally. Thrusters, reaction wheels, or something functionally similar. But that introduces a deeper problem. Such systems require power. And if it has power, where is that energy coming from? Several scientists pointed back to the perihelion event, the thermal and magnetic surge, as the likely source. If 3I Atlas harvested and stored solar energy, this could be its first visible application, a stabilization maneuver after reconfiguration. The timing fit perfectly. The object's brightness spike had ended 48 hours before the rotation change began, suggesting a transition period between charging and activation. What reinforced this theory was how precise the rotation became afterward. By November 16th, the object's light curve had stabilized to a perfect 2-hour cycle. No drift, no irregularity, no measurable precession. That kind of rotational stability doesn't occur naturally. Even metallic asteroids spin unevenly due to surface mass imbalance. 3I Atlas somehow had achieved equilibrium. The reorientation also altered its trajectory slightly. According to orbital analysts at JPL, the shift caused a small but detectable change in vector, about 0.003 degrees relative to its pre-perihelion outbound path. On a human scale, that's microscopic. But over millions of kilometers, it represents a course correction of nearly 1,000 kilometers. One researcher described it simply: it adjusted itself. Radar mapping further revealed that the radar reflectivity of certain surface areas had increased while others dimmed. The geometry suggested a smooth, flat section, now facing toward the sun, as if 3I Atlas had deliberately repositioned to optimize solar exposure. That idea resonated with those proposing the energy harvesting hypothesis. Perhaps the object had oriented itself into a sustained power collection mode, similar to how solar panels align with incoming radiation. There was another, subtler clue. Around the same time, radio telescopes scanning the region picked up brief, low-frequency bursts. 3 in total, each lasting less than a second. They weren't signals in the conventional sense, more like broad-spectrum pulses. Their timing, however, was exact. Each pulse coincided with the peak of the object's rotational alignment. Whether coincidence or not, it hinted at synchronization. The reorientation event also reawakened debate over its internal structure. The absence of thermal gradients during the maneuver meant the change wasn't caused by internal heat imbalance. Something mechanical must have driven it. A mass shift, a gyroscopic stabilization, or a system we can't yet identify. The object behaved less like a tumbling rock and more like a vessel correcting its attitude after a high-energy encounter. By November 17th, the reorientation had ended as abruptly as it began. The light curve flattened, the radar reflections normalized, and the trajectory resumed steady outbound motion. But the implications lingered. If this was truly a maneuver, then it wasn't the first. It was just the first we caught clearly. A few archival analysts began re-examining earlier data, looking for smaller overlooked adjustments in 3I Atlas's path months before perihelion. And to their astonishment, they found them. 2 minor deviations, one in late June, another in early September, both subtle enough to be dismissed at the time. When plotted together, they form a chain of precise course corrections leading directly to its perihelion alignment point. In other words, 3I Atlas may have been steering long before anyone noticed. This realization sent quiet shockwaves through the small community of astronomers who had followed the object since its discovery. If true, then its trajectory toward the sun, once believed to be gravitational coincidence, might have been deliberate. The maneuver window described months earlier suddenly made sense. The object could have used the sun's proximity to mask or power a complex sequence of internal activations. Publicly, institutions downplayed the finding. Official statements referred to post-perihelion dynamic relaxation, a term vague enough to imply random rotation without acknowledging control. But in private, few still believe this was chance. If 3I Atlas can control its orientation, it means it can control what instruments can see. It can choose when and how to reflect light, when to hide thermal emissions, and when to reconfigure its trajectory. That transforms it from a passive interstellar visitor into an active participant in its own journey. For decades, humanity has searched for signs of non-natural motion, something not governed solely by physics. We've called them techno-signatures, artifacts, anomalies. Most turned out to be illusions. But this isn't an illusion. It's motion with purpose. By the time November 18th arrived, the reorientation event had been fully catalogued and quietly archived under restricted access. The conclusion, written in understated language, captured the gravity of the moment. 3I Atlas exhibits controlled rotational realignment inconsistent with inert body dynamics. That's as close as any official record has come to admitting the unspoken truth. And as the object steadied itself and began its slow drift away from the sun, a new pattern started to form. Faint rhythmic reflections detected at regular intervals, like a mechanical heartbeat echoing through space. The source of those pulses would soon become the next obsession. By the evening of November 18th, when 3I Atlas had fully stabilized its new orientation, the world's largest radar arrays began to pick up something no one could explain, a faint but repeating signal embedded in the return echoes. It wasn't a transmission in the traditional sense. There was no frequency modulation, no carrier wave, no encoded message. It was a rhythm, an organized repetition buried in the radar reflections themselves, as if the object's surface were responding to every ping in a slightly different, deliberate way. It began as a curiosity at the Arecibo successor network in Puerto Rico. Engineers running post-processing on the radar, bounced from Goldstone, noticed a peculiar symmetry in the reflected pulse train. Normally, radar reflections scatter chaotically. The tiny irregularities of a rock's surface distort the returning signal, creating random noise. But 3I Atlas was different. Its echoes came back structured, repeating every 19.66 seconds, each return with a fractional delay pattern matching the previous one within 5 microseconds. At first, the team thought they had stumbled on a software loop, a calibration artifact. But after cross-checking with data from the Canberra Deep Space Complex, located halfway around the world, the same rhythmic sequence appeared at the exact same phase interval. 2 independent stations, separated by 10,000 kilometers, detecting identical echo rhythms from the same object. That's not coincidence. NASA's Jet Propulsion Laboratory immediately flagged the anomaly for internal review. Analysts began filtering out atmospheric noise, solar interference, and terrestrial reflections. The pattern remained, faint but coherent. Like a heartbeat faintly drumming under layers of static, the rhythm was precise, mechanical, and unwavering. When plotted across the full observation window, the pattern revealed something even stranger. Every 12th repetition, the amplitude dropped slightly, a recurring dip at perfect intervals, suggesting a 12-1 modulation cycle. Nothing in nature behaves this way. The reflections were changing themselves, not passively, but responsively. It was at this point that some scientists began to suspect what no one dared say out loud. The object might be answering, Radar doesn't just record echoes, it stimulates them. The transmitted signal hits a surface, bounces back, and we read what returns. If the target reflects light or radio waves differently each time, it can create an illusion of modulation. But what Goldstone recorded wasn't random reflection. It was reactive variance, meaning the reflection changed based on the timing of the incoming signal. To verify, engineers varied the ping rate by a fraction of a second. When they did, the echo shifted accordingly, compensating to maintain its rhythm. That's when the term adaptive reflection appeared in internal notes. 3I Atlas wasn't just reflecting radar, it was synchronizing with it. By November 19th, other observatories began testing the phenomenon independently. The results were consistent everywhere. A faint repeating pulse sequence embedded in the radar echo with minor phase shifts depending on frequency band. The repetition remained constant, 19.66 seconds per cycle, with every 12th echo dipping in amplitude. A pattern like that cannot emerge accidentally. It implies either structural resonance, a physical vibration that interacts with radio waves, or deliberate modulation. If resonance, then the object must contain internal cavities or systems oscillating at precisely that interval. If modulation, then it's controlling its surface reflectivity with astonishing precision. ESA's engineering division proposed a radical explanation. The 19.66-second rhythm could represent a feedback mechanism, an internal system adjusting to external electromagnetic input, possibly for energy stabilization. In essence, radar pings may have triggered a kind of resonance loop, allowing 3I Atlas to calibrate itself through the signal it received. The more daring voices inside the analysis teams pushed further. They suggested the object wasn't calibrating, it was communicating, not with us, but with itself. The radar pulses might have provided an external stimulus, prompting internal subsystems to synchronize. Each echo, therefore, wasn't a response to us, it was a self-test mirrored outward through reflection. But there's a detail that few outside the research circles know. That 19.66-second interval had appeared before. During perihelion, thermal sensors aboard the solar orbiter recorded 3 symmetrical heat pulses, spaced exactly 19.66 seconds apart. The recurrence of that timing weeks later couldn't be coincidence. Whatever process produced the thermal pulses near the Sun was now repeating as a radar modulation deep in interplanetary space. When this connection was made, it changed everything. If 3I Atlas's heat signatures, orientation shifts, and radar echoes all shared the same base timing, it suggested a unified operating cycle, a pulse rhythm. Machines have cycles, natural bodies do not. The discovery triggered immediate coordination between NASA, ESA, and Japan's JAXA observatories to perform synchronized radar sweeps. On November 20th, all 3 networks pinged the object at precisely calculated intervals. The result was chilling. The reflected rhythm adjusted again, shortening its cycle slightly from 1966 to 19.3 seconds, as though responding to the combined frequency of the 3 signals. At that point, the term echo synchronization entered official documentation. It was the first time any interstellar object had demonstrated apparent phase-locking behavior, the ability to maintain timing coherence with external input. Still, the data could not conclusively prove intelligence or control. It might simply be a natural resonance structure reacting electromagnetically, but even if so, it would have to be a structure unlike any known comet, asteroid, or fragment. An object capable of sustained oscillation, frequency matching, and amplitude regulation across millions of kilometers. To verify the consistency of this heartbeat, the Chinese Fast Radio Telescope joined the campaign. FAST detected the same 19.3-second echo sequence, but with an added detail, an ultra-low frequency undertone barely above cosmic background noise. It wasn't a transmission, it was a vibration, a faint modulation in phase coherence that slowly decayed between pulses. When converted to audio frequency for analysis, it resembled a deep, distant thrum. Not noise, not random, but rhythmic, deliberate. The analysts who listened to it in playback described it as the sound of machinery breathing. No agency has released this data publicly. Official press statements refer to it as a non-random radar resonance. But the internal consensus forming among those who've seen the numbers is far less cautious. The object isn't dead. It isn't dormant. It's active and for the first time interactive, because the deeper question now isn't what 3I Atlas is made of or how it moves, but why it appears to respond to observation itself. Some theorists believe the radar pulses acted as a catalyst, stimulating systems that had remained dormant since perihelion. Others think the synchronization was intentional, a test of the environment, as if the object were measuring us as we measure it. Either way, the data doesn't lie. 3I Atlas hears. By November 21st, when the global network concluded its synchronized sweeps, one final anomaly appeared. As the last radar ping was transmitted, the echo rhythm abruptly ceased. No more pulses, no more modulation, total silence. It didn't fade out. It stopped cleanly, as though someone had flipped a switch. For nearly 36 hours afterward, every observatory reported a void at the object's coordinates. A perfect radar blackout. No reflections, no scatter, no noise. Then late on November 22nd, the echoes returned. Steady, natural, unmodulated. The heartbeat was gone, but the timing of its disappearance was undeniable. It stopped exactly when the Earth stopped transmitting. The official reports end there. The data was archived, sealed, and labeled as pending analysis. But those who've seen the full telemetry say something else quietly, that the final echo sequence was an T-blank. Hidden inside the last return was a single perfectly symmetrical pulse, stronger than all the rest, delayed by exactly 19.6 seconds. Not a reflection, a reply. In the early hours of November 23rd, the International Asteroid Warning Network detected something it had never logged before. 3I Atlas was no longer moving as gravity dictated. Its outbound path, which should have followed a predictable arc away from the sun, had shifted by a fraction of a degree. But the nature of that shift told a story no one was prepared for. It wasn't a drift. It wasn't a correction caused by heat or radiation pressure. It was a controlled deviation. Every major observatory across the network rechecked the data, convinced it was an artifact. It wasn't. Radar readings from Goldstone, photometric measurements from La Palma, and optical tracking from the VLT all confirmed the same result. The object had accelerated slightly, then slowed down again, performing what looked like a smooth, intentional adjustment lasting just over a minute. It rose out of the ecliptic plane by a tiny angle, enough to alter its long-term trajectory. The maneuver was silent, invisible, and completely unexplainable. Solar wind pressure couldn't have caused it. There were no outgassing trails, no exhaust plumes, no material shedding. The surface temperature remained constant throughout the event, showing none of the thermal asymmetry that would accompany a natural jet release. Whatever force moved 3I Atlas came from within, and it operated with surgical precision. As the telemetry streamed in, agencies around the world realized this was no longer a theoretical debate. For months, the object had defied categories, heating itself, fragmenting, brightening, silencing, responding to radar. But motion like this crossed a threshold. In orbital dynamics, an object that changes speed without losing mass is an active body. Something had initiated thrust, however small. Throughout the day, encrypted channels linked NASA's Jet Propulsion Laboratory, ESA's Coordination Center in Darmstadt, and Japan's Solar Sea Mission Control. The tone of communication shifted from analysis to containment, Observers were instructed to maintain constant radar lock, but to release no public data until the new orbit could be modeled. The reason was simple. Even the smallest propulsion event implies direction, and direction implies decision. By late evening, the new trajectory was confirmed. 3I Atlas was rising gradually above the solar system's orbital plane toward the region Earth would occupy weeks later. It wasn't an interception path, but it was converging. The object was no longer following a natural curve out of the inner system. It had selected a new course. For the first time in the history of interstellar tracking, the phrase non-ballistic motion appeared in a formal observation log. It meant what everyone feared it meant: movement not governed by gravity or chance. The event lasted just long enough to be unmistakable. It began with a smooth acceleration, held steady for roughly 90 seconds, then tapered off into silence. No stutter, no random impulse. The velocity curve was almost trapezoidal, the kind of profile produced by controlled thrust rather than chaotic venting. After the maneuver, 3I Atlas emitted a faint electromagnetic haze, a soft bloom that expanded briefly before fading. It resembled a residual plasma field, like something momentarily ionized the surrounding space. Within minutes, the haze vanished, leaving behind the same spectral silence that had defined the object since perihelion. Observatories across Europe and the Americas re-aimed their instruments immediately. But the object's brightness and reflectivity remained unchanged. Whatever had happened left no physical trace, no debris, no visible reaction. It had moved and then it had stopped, as if acknowledging detection before retreating into stillness. In the hours that followed, more anomalies surfaced. A second impulse occurred barely a day later, this time shorter, just over 30 seconds, and oriented perpendicular to the first. The vector adjustment was small but precise. Once again, no visible cause. Two maneuvers, two perfect corrections, both executed with identical smoothness. By then, the realization had set in. 3I Atlas was capable of repositioning itself. Whether through electromagnetic propulsion, internal mass shifting, or an unknown process entirely, it had demonstrated control over its motion. It was not drifting, it was navigating. Across the private research networks, astronomers compared notes in quiet disbelief. Some still searched for natural explanations: plasma drag, gravitational resonance, outgassing hidden by reflectivity, but none could reproduce the motion profile. Others, less vocal, began to accept the unspoken truth that the object's behavior now matched nothing in natural celestial mechanics. After the second maneuver, all radar stations detected a subtle delay in the returning echo, as if the object's reflective surface had briefly realigned. When plotted against time, the delay formed a shallow wave pattern that slowly decayed back to normal. It was almost as if 3I Atlas had adjusted not just its path, but its external orientation, a post-burn stabilization. The network concluded that night with a directive that would never appear in public logs. Maintain silence until pattern repetition is confirmed. It meant no press releases, no new orbital diagrams, no commentary. For now, the official record would freeze the object where it last appeared, suspended on paper in a trajectory that no longer existed. Behind closed doors, a different conversation began. Some of the most senior engineers in deep space navigation reviewed the telemetry and quietly admitted what others only hinted at, that the acceleration profile resembled the kind used to correct a spacecraft's attitude after a gravitational assist. The resemblance was exact. The implications are impossible to overstate. An interstellar body, presumed inert, had just executed a maneuver indistinguishable from those used by human technology. Smooth acceleration, precise cutoff, zero waste. It didn't just move, it decided to move. The night sky remained unchanged to the naked eye. To anyone looking up, nothing had happened, but across the encrypted monitors of observatories from Pasadena to Darmstadt, the numbers told a different story. The moment when a cold, silent object from beyond the stars proved that it was not a passenger of physics, but its own pilot. And then, just as quickly as it had moved, it went quiet again. No thermal spikes, no radar echoes, no new adjustments. 3I Atlas drifted outward, steady, inscrutable, as if conserving energy for whatever came next. That next moment arrived sooner than anyone expected, not from the object itself, but from the sun. A sudden solar eruption, unpredicted and violent, tore through the inner system days later. But even before the flare left the solar surface, 3I Atlas was already shifting its trajectory again. Seconds before the eruption began, as if it knew. The event began on November 26th. A violent coronal mass ejection erupted from the sun's southern hemisphere, sending billions of tons of plasma arcing into space. It was one of the most powerful solar ejections of the year, fast, chaotic, and unpredictable. The eruption wasn't directed at Earth, but it carried enough energy to disrupt magnetic fields across the inner system. Yet, before the flare even registered on solar monitors, 3I Atlas had already begun to move. At 7:41 UTC, 27 seconds before the first wave of the eruption was detected by NASA's Solar Dynamics Observatory, the object performed a subtle lateral adjustment, a half-ms shift away from the solar equator. It was small, barely measurable, but perfectly timed. The telemetry showed the change began before the Sun's surface explosion was visible from any solar observatory. In other words, it reacted to an event that hadn't yet happened from its vantage point. For the team still tracking its trajectory, that timing was impossible to rationalize. It either anticipated the eruption or it sensed precursors that no human instruments had yet detected. The odds of coincidence were effectively zero. Within minutes, the sun released a full coronal wave that spread outward through the solar wind, briefly overwhelming magnetometers aboard Stereo A and the Parker Solar Probe. During the disturbance, most instruments went blind, all but one. ESA's solar orbiter managed to maintain partial telemetry and captured something extraordinary. As the coronal material raced outward, it appeared to bend slightly around a small void, a distortion in the flow precisely where 3I Atlas was traveling. This observation triggered the first reference to what scientists quietly began calling the swan factor. The name came from a newly discovered comet, C2025 R2 Swan, which had entered the inner system from the opposite direction just days earlier. Swan's orbit, by pure geometry, mirrored that of 3I Atlas, both objects approaching the Sun from opposite sides of the ecliptic, both reaching perihelion within 48 hours of each other. At first, Swan seemed unremarkable, a typical bright comet venting jets of vapor as it neared the Sun. But its motion soon drew attention for a different reason. Its orbital plane wasn't random. It intersected the exact coordinates 3I Atlas had crossed 2 weeks earlier. The symmetry was eerie, like two trajectories mirrored across the solar equator. No one wanted to call it synchronization, but that's what it looked like. In the hours following the solar eruption, both bodies, Swan and 3I Atlas, behaved anomalously. Swan's tail lengthened far beyond predicted limits, glowing with an intensity nearly double that of standard cometary models. Meanwhile, 3I Atlas on the opposite side of the Sun remained perfectly stable. No heating, no brightness fluctuation, no disruption from the passing plasma storm. The flare had hit everything in its path, yet the interstellar object remained unaffected, as if shielded. When data from Parker Solar Probe was decoded, it showed that plasma density around 3I Atlas dropped sharply during the CME, forming what analysts called a shadow bubble. The solar wind simply avoided it, flowing around rather than through. The object didn't resist the wave, it redirected it, behaving like an electromagnetic lens. The only comparable phenomenon in physics would be magnetic field shaping, a technique used in controlled plasma containment. What made it even more unsettling was the near-simultaneous response of Swan. As the solar flare swept past, Swan's luminosity flickered in intervals, matching 3I Atlas's known 19.6-second rhythm, the same timing as the echo pulses detected days earlier. Two bodies on opposite sides of the sun resonating to the same invisible pattern. The probability of that synchronization being random is virtually zero. It implied that both objects were responding to the same stimulus or to each other. By November 27th, researchers began to suspect the two objects were not independent. Swan's orbit appeared gravitationally ordinary, but its behavior wasn't. Its ion tail exhibited structured striations, faint parallel bands of alternating brightness, perfectly spaced, perfectly timed. The bands propagated outward like encoded ripples traveling at near constant velocity. When plotted, the intervals between them matched the radar echo pattern from 3I Atlas exactly. The possibility forming among analysts was quietly alarming. Swan might not be just another comet. It might be a counterpart, a relay, or even a control point linked to 3I Atlas's activity. The sun, they speculated, could have been the synchronization medium, a point of electromagnetic convergence that connected both through solar resonance. For decades, the concept of solar resonance, the idea that large-scale magnetic fields could carry structured signals, existed only in theory. But now, telemetry was showing behavior consistent with a real, functioning example. During the CME, data packets in the solar plasma exhibited repeating low-frequency modulations that corresponded exactly to the positions of both objects. They weren't messages in any conventional sense, but they were structured. The sun itself briefly had become a conduit. The network tracking centers noticed something else. Following the eruption, the plasma field that surrounded 3I Atlas pulsed 3 times, slow, even intervals, then went still. Each pulse coincided with a measurable brightness increase in Swan-S coma on the opposite side of the system. It was as if energy was being transferred across the sun, one object responding to the other. At this stage, all data was moved off public servers and into restricted archives. Official statements mentioned a temporary solar interference anomaly, but internally, scientists knew what they were looking at. A system of two bodies acting as if linked, behaving with a timing precision unmatched in any natural context. Over the following week, the correlation deepened as 3I Atlas moved outward. Swan's orbit decayed slightly faster than predicted, as though the smaller comet were losing momentum while the larger object gained it. Energy conservation pointed in only one direction. Swan was slowing down, and 3I Atlas was speeding up. To those watching the numbers, the pattern was undeniable. Energy was not disappearing, it was transferring. That's what the Swan factor came to represent. The first measurable sign that 3I Atlas might not be acting alone. Two separate bodies linked through solar proximity sharing motion, light, and possibly charge, an interaction that no known law of celestial mechanics can explain. In the wake of that discovery, observatories began looking for other anomalies. Smaller comets, minor outbursts, anything behaving in sync. A few faint candidates appeared, but none matched the precision of the Swan correlation. For now it remained unique. Two travelers on opposite sides of the sun, one bright and chaotic, the other silent and deliberate, bound by an invisible thread. And when the solar storm subsided and the heliosphere calmed, a new pattern began to emerge. Instruments tuned to monitor radio quiet zones detected narrow-band fluctuations centered not on 3I Atlas, but in the empty space between it and Swan, a midpoint roughly halfway across the solar line. The signal wasn't noise, it had order, a faint oscillation that pulsed with mathematical regularity. For those listening closely, it felt less like static and more like a handshake. Whatever connected the two had finished calibrating. Something had linked across the sun, stabilized, and gone quiet again. But as the solar wind cleared and the object continued outward, another mystery followed in its wake. A blank stretch of sky where telemetry vanished, as if an unseen field had swallowed every signal. It wasn't absence anymore. It was blackout. By the beginning of December, the global network tracking 3i Atlas began to fail, not from malfunction, but from absence. Data streams that had been continuous for months went dark one by one, as if the object had crossed a threshold beyond visibility, not in distance but in interference. Ground-based telescopes reported clean skies where it should have been. Radar echoes faded into static, and deep space antennas returned nothing but uniform background noise. 3i Atlas hadn't vanished. It had erased itself from detection. The blackout began suddenly on December 2nd at 03:02 UTC. The Goldstone radar station transmitted its routine ping. For weeks, it had received faint but consistent returns, the signature pattern used to update the trajectory. This time, there was no echo, only silence. Within hours, ESA's solar orbiter lost telemetry as well, its instruments unable to distinguish any reflected light from the predicted coordinates. When the Very Large Telescope attempted to reacquire the object visually, it saw only the faint glare of the solar wind, empty space. Analysts first assumed a positional error. Perhaps the object had shifted slightly out of the observation corridor, but within 12 hours, every station across 3 continents confirmed the same void. The blackout was global. No optical, radar, or infrared system could detect 3i Atlas in any spectrum. Even the sensitive gravitational perturbation data from Gaia, which should have registered its pull on nearby bodies, flattened to zero. The disappearance was too precise to be natural. The object had not merely drifted beyond our instruments. It had suppressed every measurable signature. Reflectivity, radio emissions, even its gravitational trace appeared dampened. The concept of gravitational damping doesn't exist in physics. Yet, the data behaved as if its mass had ceased to interact normally with the surrounding field. Then came the strangest detail. During the same period, the background noise of space, the constant hum of cosmic radiation and solar interference, changed. In every region where 3i Atlas had last been tracked, noise levels dropped slightly, forming a soft, circular region of stillness, expanding outward at roughly the object's velocity. It was as if it had left behind a moving bubble of silence, a zone where the universe itself went quiet. Parker Solar Probe detected the edge of that silent zone on December 3rd. For several hours, its particle sensors recorded unusually low plasma counts, like a temporary cavity in the solar wind. Within that void, communication signals weakened, data packets delayed, and time synchronization errors appeared across the probe's onboard systems. Whatever field surrounded 3i Atlas, it interfered not only with energy and light, but with information itself. By December 4th, the blackout had spread to nearly 1 million kilometers around the object's last known position. Astronomers began calling it the ecliptic void. No telescope could penetrate it, and no instrument could confirm what lay within. Yet inside that region, faint disturbances hinted at continuing motion. Small fluctuations in the solar wind, consistent with a body still traveling outward. For those who had followed its path since discovery, the realization was sobering. The object had not disappeared. It had transitioned from visible to invisible, from measurable to abstract. Whatever systems had awakened during perihelion had now completed their sequence. The silence that followed was not loss, but conclusion. In the days that followed, the network servers filled with static. The last confirmed radar echo from November 30th was replayed endlessly. A short burst of data, now treated as an artifact of contact. The world's observatories moved on to other priorities, other comets, other transient lights. But for those who had seen the numbers, the blackout wasn't the end of a mission. It was the signature of withdrawal. 3i Atlas hadn't stopped broadcasting, it had stopped allowing us to listen. And in the weeks after, as the void drifted steadily away from the inner system, some instruments began to pick up something faint beyond it. Not a signal, but an absence with rhythm. A pattern in the silence repeating every 19 seconds. The same timing as before, carried now by nothing visible, nothing measurable, yet still there, just beyond the noise floor of detection. It was as though the object hadn't left the solar system. It had simply changed the terms of observation, turning its silence into communication, its disappearance into a kind of message. When the last trace faded from our senses, only one thing remained constant. The math, the trajectory, even after blackout, still pointed outward along a perfect curve, unbroken, unaltered, and accelerating slowly beyond the sun's reach. And though it's no longer visible, the calculations show that sometime in late 2026, that path will intersect the outer boundary of our heliosphere. The invisible frontier where the sun's influence ends and true interstellar space begins. No one knows if it will reactivate then, or if we'll ever detect it again. But those who tracked its final movements understand one truth that can't be undone. For a brief moment, we witnessed an object that behaved as if it knew we were watching, and then it turned away. Tonight, 3i Atlas is somewhere beyond the inner planets, moving quietly through the cold. Its trajectory is still calculable, but its presence is gone, absorbed into the background hum of the cosmos. What began as a faint discovery, a distant object on a long elliptical path, has evolved into one of the strangest events in modern astronomy. A body that heated itself, reoriented, gained mass, responded to radar, and finally disappeared in complete, deliberate silence. The numbers remain, the timestamps, the echoes, the coordinated anomalies, all consistent, all real. But every attempt to explain them collapses under one unanswered